Hi, welcome to Unlock Layout and Design YouTube channel. This is part 2 of semiconductor resistors. So today we are going to discuss about different types of resistors like diffusion resistors, N-well resistors, poly resistors, etc. And we are going to look into how do we form a large resistor. So there is a serpentine form that we are going to look into, and then we are going to speak about important topic mismatch, in which we are going to discuss about systematic mismatch, random mismatch, gradient mismatch, process variation. And to counter these mismatch effects, we are going to look into different matching techniques like common centroid matching, adding dummies, and we'll also look into some examples. Finally, we'll summarize the entire discussion. Let's look into the general structure of a resistor. So this is a strip of a material having some resistor, but how do I use it as a resistor? So what I do is I make a contact here, and then connect it to the external world using a metal. So the region between these two contacts acts as a resistor. So this diagram over here actually is nothing but the same thing on the top view. This is the contact, this is the contact, and this is the body of the resistor. And this is the length of the resistor, and this is the width of the resistor. The diagram you see below is nothing but the top view of the same resistor seen in a CAD tool. Now we'll discuss about different types of resistors. So first one we discuss is a diffusion resistor. So as we discussed earlier, so between two contacts, whatever is the material that acts as a resistor. Here I am using a N plus material as a resistor, or this is a N plus diffusion resistor. Similarly, between these two contacts, I have P plus material, and this acts as a P plus diffusion resistor. I can use the N-well itself as a resistor. So how do I do that? I have these two contacts. What do I do is I put a N plus block so that it connects well with the N-well, and this entire N-well acts like a resistor. So the resistivity at the surface interface is like relatively lesser. So what I do is I pinch it off using a P plus material so that the resistivity increases. So this forms a pinched N-well resistor. N plus diffusion resistor has a relatively lesser resistance as compared to a P plus diffusion resistor. Now we'll discuss about a undesired effect called the voltage coefficient of a N-well resistor. Whenever a N-well is formed in a P minus substrate, a PN junction as shown here is formed. And whenever a PN junction is forward biased, the active area is very high, and then there is no depletion region. Whereas when the same junction is reverse biased, the active region decreases and the depletion region increases. Same way, when I have a resistor here and this is connected to say 3.3 volt and this is connected to say 1 volt, the depletion region very close to the 3.3 volt contact is very high, and the depletion region at the other contact is which is having 1 volt potential, the reverse bias is minus 1 volt, and it has a narrower depletion region. On the other side, the active region near this terminal is higher, and the active region towards the other terminal is very less, making the channel ununiform, and it creates a different resistance, and this resistance is totally proportional to the applied voltage, and this is called voltage coefficient. One more undesirable effect is formation of a capacitor. So whenever we have a PN junction which is reverse biased, it always gives rise to a parasitic capacitance. That is the capacitance which we have to deal with. Now we will discuss about different types of resistors, that is a metal resistor and a MOSFET resistor. We have seen how we can use NVL as a resistor, and now this is a poly which can also be used as a resistor, and then these transistors are connected to the other portion of the circuit using metal 1, metal 2, metal 3, metal 4, metal 5, etc. So such a process is called 1p 5m, which has one poly 5 metal layers. Here I am using this portion as a resistor in metal 3. So metal resistors have very low sheet resistance of few milliohms per square. So this is suitable only when we use resistors for a very small value. Let's now look into the MOSFET resistor. Whenever MOSFET is used in the linear region, it can act as a resistor. In this example, this is a common source amplifier with a resistor load, and this MOSFET is used in the resistive region, and that is decided by the bias conditions. And we can also use in the LDO, we can use a MOSFET as a variable resistor. So in this case, this is a compensation resistor for the pole zero tracking method of compensation. In this, based on the VGS, the resistance value varies. Now we'll look into one more type of resistor which is called as polyresistor, which is widely used inside the chip. The MOSFET gate is nothing but a polysilicon or a poly which is abundantly used as a resistor. Now this is the body of the resistor. We can add some dopants so in order to reduce the sheet resistance of a poly resistor. Now let's see what is a salicide process. Silicide is a material which is used to lower the resistance of the source, drain and the poly gate. So whenever source, gate and drain are formed, we will on top of that we'll add this silicide material and to lower the sheet resistance of these areas, the poly gate and the source and drain. So whenever this process is a self-aligned process, then it is called salicide process. So here you can see the gate, drain and the source, the drain, source and the gate are having the silicide layer. That's how the resistance is reduced. So our intention is to use poly as a resistor. So whereas by salicide process, the sheet resistance actually reduces. So whenever I have a MOSFET, I have no objection to lower the sheet resistance. Whereas when I use the same poly as a resistor, I don't want the resistance to reduce. So what I do is I put a blocking layer across this during the salicidation process. That's how my sheet resistance is protected to be higher. So in this diagram also you see, so this is a material which is of polysilicon and I have a salicide block layer here which prevents the silicidation process for the polyresistance. So this is another top view of the resistor, which is like having a RPO layer, which is nothing but a resist protection oxide layer, which again prevents this to be salicided. Okay. And some processes call this same thing as sab layer or silicide block layer. And as I told you earlier, we can put some implants like P plus implant, N minus implant, N implant, P implant in order to change the resistivity of the uh, polyresistor, and I can also use a high resistance implant in order to increase the resistivity of the polyresistor. But mind you that it comes at a cost, and this generally has a extra mask and comes at a cost. And here we observe that a non-silicided poly has a higher sheet resistance and a silicided poly has a lower sheet resistance. Whenever I need a large value resistor, I use a serpentine form of the resistor which looks like this. So here the resistor has got many bends and it looks like a serpent. That's why it's called as a serpentine resistor. There is a disadvantage here at the corners. There is a 90-degree bend and here 56% of the square is utilized in conduction and hence the resistance increases. So how do I overcome this problem? So I have many strips of such resistors and I connect them instead of 90-degree bends. What I do is I use metals to connect them. So that way my resistance and the 90-degree bends are like very minimal. It is the same thing shown here as well. So one more way of tackling the problem is instead of 90-degree bend, I'll use 45-degree bends so that the resistance is not very high. The next important concept is the mismatch. When I fabricate, say, 100 resistors of 1K, not all of them will be 1K. The reason is there would be some mismatch. So there are different types of mismatch. We'll analyze each one of them in detail. The first type of mismatch is called systematic mismatch. This type of mismatch is introduced by the designer or the layout engineer, and this can usually be avoided. How do we avoid that? We'll see it in a minute. The other type of mismatch, as the name says, is random mismatch. This random mismatch is because of variation in process, parameters, and lithography. This is beyond designer's control and should take into account these variations while designing. So designers should take into account these variations while designing. And the third one is a gradient mismatch. So whenever we have a chip which is of higher length and width, we have some gradients. So for that reason, we'll have a mismatch and we'll look into the gradient mismatch in much more detail. Apart from these three mismatches, we also have something known as the process variation. So we will introduce this process variation will introduce error homogeneously for all resistors on the chip. Suppose I have 100 resistors of 1K, almost all of them will become like 1.2K or 0.8K. This kind of variation is known as process variation. Now let's try and understand what is systematic mismatch in a greater detail. Suppose I have an amplifier which needs a gain of 2. I need RF to be 200 ohms and Rin to be 100 ohms so that the gain is 2. Now how do I get these resistors? So let's assume this resistor having length L and W width has a resistance of 100 ohms. Now I take another piece of resistor having the length 2L and width same W. Now what is the resistance? The resistance is now 200 ohms. Let's stop and look into some more details. What have we missed? We have missed the contact resistance, which will be generally around 5 ohms. So each contact will be 5 ohms. So the resistance now is not 100 ohms, but it is 110 ohms. Whereas here, what is the resistance? The resistance is 200 plus 10 ohms, which is 210 ohms. Now if you take the ratio, it is 210 ohms divided by 110 ohms. This definitely is not equal to 2. Now I'll change the way I do the layout of this. I use two segments having each one having length L, width W, and then connect them in series as shown. Now each one has two contact resistors so that the total resistance now is 200 ohms plus 20 ohms. So that comes to 220 ohms. Now if I take the ratio, it is 220 ohms by 110 ohms, which comes to the same gain as planned, which is 2. So this is how we reduce systematic mismatch. So it is definitely within our control, and by good practice of design and layout, we can eliminate or avoid this systematic mismatch. Let's now look into what is known as random mismatch. Suppose I need to fabricate, say, 100 1 kilo ohm resistors. So the resistors which actually get fabricated as 1 kilo ohm, say they are around, say, 50 of them. Okay, so these all have the value of 10 kilo 1 kilo ohm, sorry, 1 kilo. But this, some of the resistors have the values in between 1 kilo ohm and 1.1 kilo ohm. So in between are these resistors. Some of them, say 20 of them each, they have 1.1 and zero point 0.9 kilo ohm. So the deviation is like zero point 0.1 kilo ohm plus or minus. So when I fabricate, the rest of them have the values, say zero point 0.8 and zero point 0.7, and this one has got 1.3 and 1.2 kilo ohm. Now I intended to have my resistance to be 1 kilo ohm, but some of the samples, say 50% of them, came in the region of, like in the central region, where the resistance is almost like 1 kilo ohm, and for the others they have a deviation of like zero point 0.1 kilo ohm. Some of them have zero point 0.2 kilo ohm, and some of them have zero point 0.3 kilo ohm plus or minus. If you see, the zero point 0.3 kilo ohm is like very minimal, and zero point 0.2 is even lesser, and 1.1 or the zero point 0.1 is highest. So the center value or the intended value, say 1 kilo ohm, here is known as the mu or the mean value, and the deviation here, what you see, the zero point 0.1 kilo ohm is known as the sigma, which is called as standard deviation. Now if standard deviation is higher, that means to say that more and more samples are having higher differences, and the height of this curve reduces and the spread increases. So the sigma value should be as low as possible for the mismatches to be minimal and to get higher accuracy of resistors. So this kind of a mismatch is called as random mismatch, and this is a Gaussian distribution what you are seeing here. Normally, the random mismatch is expressed as sigma, the standard deviation, and the mean value mu. For that reason, I have introduced these terminologies here. Now let's look into what is the cause for this random mismatch. So when I form a resistor, I want it to be formed of this form. But because of line edge roughness, what happens? It gets formed this way, wherein the edges are not straight and they are very much deviated from the actual smooth surface, and it creates high resistance regions. Now, let's try and understand. If I need a resistor of 200 ohms, I can get that resistance by using 100 micron by 100 micron area, or I can even reduce the area to 10 micron by 10 micron. I still get 200 ohms, or I can even reduce it further to 1 micron and 1 micron. I still land up with 200 ohms. But which is better here? So if we see this table here, it shows around 45 ohms of resistor is fabricated by three different areas. First one is 3 micron by 3 micron, and then it is 2 micron by 2 micron and 1 micron by 1 micron. If I see the variation or the sigma here, the standard deviation, this one has got 0.5%, whereas 1 by 1, which is the least area, it has got the highest standard deviation of 3.1%. So this gives a clear indication that area matters for standard deviation and the mismatch. So it's also given by this standard deviation equation, wherein we understand that it is inversely proportional to square root of W and L of the polyresistor. So if I need a resistor with fairly good accuracy and very little mismatch, then what is that I have to do? I have to increase the area. So in order to reduce mismatch. But then there is a catch. When I increase the area in semiconductor, area is always money. Okay, I need to shell out a lot more money for getting a proper less mismatch resistance. But that's not all. Bigger area also implies a parasitic capacitance, and this capacitance will reduce the bandwidth. So random mismatch always is reduced by increasing area, but it comes with these two clauses. So we need to take care in our design. The next type of mismatch is a gradient mismatch. So what is this gradient mismatch? Let's look into it. Whenever I have an IC which is not very small, which has like a bigger length and bigger width, say some 3 mm or 6 mm even. So that time the length is quite high, and then we have a gradient from one corner to another corner. So that kind of a mismatch is called as gradient mismatch. So how do I minimize this gradient mismatch is the question. So for example, I have a gradient from this corner to this corner, and I have three resistors R1, R2, R3, all of same value, but because of the gradient, this has a higher thickness, this has a thickness of T, this has T plus delta T, and this has T minus delta T. Obviously, the resistance of this is much higher compared to the resistance of this. So this leads to a gradient mismatch. So if I want a resistor ratio, then obviously the gain will change because of the gradient. Another kind of gradient is a temperature gradient. As you can see here, I have a power device here, and then I have gradients, thermal gradients going around like this. So that time, if I put two resistors like this resistor R2 has a higher temperature gradient as compared to the resistor R1. So where can I get such a scenario? Such a scenario can be quite possible in a LDO where the pass FET is nothing but a power device, and the resistor divider for feedback can be these two resistors. So if I put the resistors, instead of placing it side by, if I place them below, then both of them experience the same thermal gradient, and that's how I can remove the gradient mismatch. Okay. As we discussed, so we have a requirement that RF by R say needs to be like gain of 2. So that means to say RF should be say 2K and Rin should be 1 kilo ohm. Suppose I place the two segments of, I'll call RF as B and Rin as A. So because of the gradient, instead of 1K, this became 0.9K, and this is still 1K, but whereas this one became 1.1K. Now the resistance A, which is nothing but Rin, is like 0.9K, and the resistor RF, which supposedly should be like 2 kilo ohm, is now 2.1 kilo ohm. So I have a gradient mismatch. So if I take the ratio, it is 2.1 kilo ohm divided by zero point 0.9, which is greater than 2. Whereas I can realign these segments and eliminate this gradient mismatch. So how do I do it? Instead of putting A at the end, I'll put A in the middle, and B, I will spread them out next to the A, both the sides. So now B together will be like 0.9k plus 1.1k, which is equal to 2k, and A is 1k. So if I take the ratio, it is 2k by 1k, and hence my gain is achieved, and I got rid of gradient mismatch. So we know that we have a gradient problem, and the solution for the gradient problem is something known as common centroid matching. Suppose I have two segments of A, I place them A and B. Then the centroid of A is here and centroid of B is here, and there the centroid is not common. Or if even if I put AB, the centroid of A is here across this axis, and the centroid of B is across this axis, and the centroids don't overlap, and that's how this is not a common centroid. Whereas if I put the segments of resistor A and B in this form, then the centroid of B is here, which is equidistant from both the centers of B, and also for A this is the centroid. So this is a common centroid matching. This is called as interdigitated matching. So whenever I have a gradient in x direction, this will take care. Sometimes the gradient can be in both directions, not only in x but also in y. That time I will use a two-dimension matching, or it's also called as cross-coupled matching, in which I arrange the segments in two rows which has like ABBA and BAAB. Now for A, this is the centroid, and for B again this is the same centroid. So this is a common centroid matching for like two dimension or. So now that we discussed about systematic, random and gradient mismatch, we also have something known as process mismatch, which is actually a uniform variation in the resistive materials. Suppose say I fabricated three resistors of 1k. So because of the process mismatch, what happened is all the three resistors got fabricated as 1.2k, or it can even be like 0.8k or something. Whatever is the variation is uniform. This doesn't affect much, and I can take care of this in my circuit technique. So if I need a gain of 2, even if they become like uniformly, if there is a mismatch which is uniform, then the resistor RF will be 2.4k and R in will be like 1.2k, such that RF by Rin is still the same as 2. I have no issue because I am using the ratio of resistors. One more problem we have is the boundary conditions of the polyresistor. During etching, this boundary can have higher variation as compared to. So if I see the B resistors here, they are saying one more polyresistor on the other side. So the etching this side and this side of these two resistors are the same, whereas if I don't put a dummy, there would be a different etching pattern at the end which will affect these two resistors. That's why what we do is we add something known as dummies, and these dummies can be left open or can be connected to some potential. So dummies are useful in order to uh, uh, reduce the variations in the boundary resistors. Now let's summarize the different topics that we discussed today. So we discussed different types of resistors like the N plus diffusion, P plus diffusion, N well, P well, pinched N well, pinched P well, and we have discussed about polyresistors. Sometimes we also have double poly processes. Then we have two polyresistors, which is the first poly and the second poly. And we also discussed the pinched N well will have a higher sheet resistance. So that is this. You can see N well has 2 to 4K, whereas pinched N well has got 6 to 8K. So we also discussed about the accuracies, the temperature coefficient and the voltage coefficient. We have discussed these parameters in detail in the first video, and I would request you to go through that first video in order to gain more clarity in these topics. We also discussed mismatches, which is like the systematic mismatch, random mismatch, gradient mismatch, and process variation, and how to counter them by different matching techniques. And we have summarized the entire topics that we discussed today. These are the references that I used for my video today. Thanks for watching this video, and if you like this video, please share and subscribe. Thank you.